The first fully implantable pacemaker worked inside a human body for only 8 hours, and that failure helped clear the path for the device that would endure. On October 8, 1958, the world crossed a line in Sweden. The first fully implantable pacemaker procedure was performed, a moment that turned an idea into a living test inside a human chest. The device itself has become one of the starkest images in the history of medicine. Components encapsulated in an empty kiwi shoe polish can. It was a breakthrough, but also a warning. After just 8 hours, the device failed. That short span captures the central problem better than any celebration could. It was not enough to make a pulse. It was not enough to fit electronics inside the body. The real challenge was reliability. A machine could be implanted, but could it keep working when a life depended on every beat? That question sits at the heart of this story. Not who had the boldest first step, but who could make the technology dependable enough to matter beyond a headline. Because in medicine, an invention is judged not only by its novelty, but by whether it stays with the patient after the operating room lights go dim. And while that Swedish procedure marked the first fully implantable pacemaker, the failure after 8 hours left the field painfully open. Somewhere else, another engineer was already focused on the same basic problem from another angle: how to create a pulse that matched the rhythm the body needed, and then how to make that pulse last. The surprise is that his route into that problem did not begin with a planned triumph. It began with a mistake at a workbench. Small, ordinary, almost embarrassing. The kind of error most engineers are trained to avoid. Part 1, the wrong resistor. And yet, from that wrong part came a rhythm that sounded uncannily right. In 1956, electrical engineer Wilson Greatbatch was building an oscillator when he accidentally installed the wrong resistor. Instead of a 10 kilo-ohm resistor, he plugged in a 1 mega-ohm one, the brown, black-green resistor. By ordinary standards, it was a serious mismatch. The part was severely overpowered for the place where it had been used. But when the circuit ran, it did something unexpected. It cycled a brief pulse, followed by a 1-second silence. The pattern closely mimicked a human heartbeat. That is the hinge of the entire story. Not a magical flash detached from real work, and not a myth about genius appearing from nowhere. A circuit behaved differently because a component was wrong, and Greatbatch recognized what that behavior meant. In the pulse and the pause, he heard a possibility, an electrical rhythm close enough to the human heart to suggest a medical use. There is a reason this moment has lasted in the telling. It compresses invention down to 2 parts that rarely arrive together: accident and recognition. Plenty of mistakes lead nowhere. Plenty of people see unusual behavior and move on. What matters here is that Greatbatch understood that the pattern in front of him was not just a malfunction. It could be a lifeline. But seeing potential in a circuit is one thing. Turning that potential into a device that can enter the body is another. An engineer can be excited by a pulse on the bench. Investors and employers hear something else: danger, cost, uncertainty, liability, years of work, no guarantee of success. So the next question was brutal and practical. Part 2, too perilous to fund. Once Greatbatch saw what that mistaken resistor had revealed, who would risk building it into reality? Greatbatch took the idea to his employer, Tabor Instrument Corp. The response was not enthusiasm. The company was unwilling to risk funding his device because they considered the pacemaker too perilous of an investment. That word matters: perilous. It captures both the financial and the human stakes. This was not a safer improvement to an existing product line. It was a medical device meant to operate inside the body, tied to the most unforgiving standard imaginable. If it failed, the consequences would not be abstract. And from the company's perspective, that made the project hard to justify. It is tempting in stories like this to cast rejection as simple blindness. But the refusal also reveals the climate around the idea. Even after the heartbeat-like pulse had appeared in the circuit, there was no smooth institutional path waiting for it. The gap between invention and acceptance was wide. For Greatbatch, that meant the project immediately became personal. If the company would not carry the risk, he would have to decide whether the idea was strong enough to carry it himself. That choice is where many inventions stop. A concept can survive an accident at the bench. It often does not survive the cold arithmetic of money, family, and time. What do you do when the thing you think could save lives is judged too dangerous to back? Do you accept that the world is not ready? Do you file the idea away and move on? Or do you make the kind of decision that can unsettle every part of your life? Greatbatch chose the hardest route. He did not just continue after work or wait for a better moment. He left the safety he had, and in doing so, Part 3, the barn gamble, transformed an intriguing possibility into a wager against failure. Determined to develop the device, Wilson Greatbatch quit his job. He used his $2,000 life savings to support his family for 2 years, and he hand-assembled pacemaker prototypes in the barn behind his house. That image has none of the polish of a corporate laboratory. No grand research campus, no well-funded development wing, no guarantee that the next prototype would be better than the last. Just an engineer, a barn, limited savings, family pressure measured in months, and a machine that had to become far more than an intriguing pulse. The barn matters because it tells us what stage this invention was truly in. It was not yet secure enough to attract confident backing. It depended on persistence in a place where persistence is expensive. Every prototype represented more than technical labor. It represented time taken from a finite reserve. And the family context matters too. The source does not describe a romantic, consequence-free leap. It says he used his $2,000 life savings to support his family for 2 years. That detail puts real weight on the decision. This was not invention as hobby. It was invention under pressure. Hand-assembling prototypes also suggests the slow, exacting character of the work. A pacemaker could not simply imitate a heartbeat once on a bench and call itself ready. It had to become a device. And a device intended for implantation demanded a level of trust that could not be improvised. In that barn, Greatbatch was not chasing a single moment of discovery anymore. He was trying to convert discovery into reliability. Meanwhile, the wider race in implantable pacing was not waiting. Others were pursuing the same goal by different routes, and the world would soon see that getting a device into the body first was only part of the battle. The deeper battle was making sure it could stay there and keep doing its job. That is why the next chapter in this story is not Greatbatch alone. It is the field around him, and the harsh lesson that the earliest triumphs could still fail almost immediately. Part 4, a field opened by failure. The Swedish team had already achieved something historic in 1958, the world's first fully implantable pacemaker procedure. That fact deserves its place. But so does the outcome. The device failed after just 8 hours. In a less honest retelling, that first implant might be reduced to a footnote because it did not last. But the failure is central to understanding what came next. It exposed the difference between possibility and dependability with almost painful clarity. A heart could be paced by an implanted device. The concept had crossed into reality, yet reality also answered back. The first version was not durable enough. This was the opening Greatbatch needed, though not in any triumphant or gleeful sense. Another team setback underscored the exact problem he had to solve. The issue was no longer whether implantable pacing belonged to science fiction. It was whether someone could make it work successfully in a way that held. That kind of moment sharpens a field. Rivalries can form around credit, firsts, and whose design deserves the future. But underneath all of that, the patient's need remains brutally simple. The pulse must continue. The device must survive beyond the first dramatic hours. Greatbatch's work then entered a world that had seen both proof and disappointment. Proof that implantation could be done. Disappointment that the device could fail almost at once. This combination changed the stakes. It made reliability the prize. And that brings us to the turning point. Greatbatch was no longer just an engineer with prototypes in a barn. To move forward, the work would have to connect with surgery, with actual patients, and with the moment when theory finally meets the body. After years of personal risk, the question became immediate. Would his device succeed where the first fully implantable attempt had so quickly fallen short? In 1960, the Chardack-Greatbatch pacemaker had its first successful human implantation. That sentence is compact, but it carries the weight of everything before it. The mistaken resistor, the employer's refusal, the drained savings, the prototypes built by hand, the field-wide warning delivered by an 8-hour failure in Sweden. The name itself matters too. Chardack-Greatbatch marks this as collaboration rather than a lone man myth. Whatever the rivalries and pressures around early clinical adoption may have been, the successful implant is attached, in the verified record provided here, to more than one name. Success in 1960 did not erase what others had accomplished earlier. The Swedish team still holds the first fully implantable procedure in 1958, but the successful human implantation of the Chardack-Greatbatch pacemaker marked a decisive recovery in the story of implantable pacing. It suggested that the technology could move from dramatic experiment toward dependable treatment. This is the point where Greatbatch's gamble begins to justify itself. Not because one operation ends all doubt, but because it proves that his years of work in the barn had reached the clinic in a meaningful way. The idea born from an accidental resistor was now no longer merely persuasive in theory. It had entered human use successfully. And still, another question remained. Even with successful implantation, how long could such devices keep working? In a field defined by every heartbeat, longevity is not a side issue. It is the issue that decides whether patients receive a temporary reprieve or a durable solution. So, the comeback was real, but incomplete. Greatbatch had helped deliver a successful implant. To secure that victory in any lasting sense, the device would need endurance. Without that, the same old vulnerability would return, one patient and one battery life at a time. The final stage of his contribution would come later, and it would address precisely that hidden weakness. Greatbatch later vastly improved device longevity by inventing the lithium iodide battery in the 1970s. That development completes the arc of this story. The earliest surprise in 1956 was a rhythm, a brief pulse followed by a 1-second silence that mimicked a heartbeat. The major clinical success in 1960 showed that an implantable pacemaker could be used successfully in a human patient. But the battery innovation in the 1970s speaks directly to the deepest lesson of the 8-hour failure that opened this film. A pacemaker must last. This is why Greatbatch's legacy cannot be reduced to a single accident with a resistor, however memorable that moment is. The accident revealed a path. The refusal by Tabor Instrument Corp. Forced a personal gamble. The work in the barn turned possibility into prototypes. The successful human implantation of the Chardack-Greatbatch pacemaker proved the device could matter in the clinic. And the lithium iodide battery vastly improved longevity, strengthening the technology's claim to reliability. Put together, these facts describe more than an isolated invention. They describe a progression from pulse to implant to endurance, and they also place Greatbatch inside a broader, more honest history. The first fully implantable pacemaker procedure in Sweden in 1958 remains a landmark, even though its device failed after 8 hours. The successful human implantation in 1960 marks another landmark. The later battery improvement marks yet another. The history is not one clean flash of genius. It is a chain of advances, setbacks, and repairs. Still, there is something almost poetic in the beginning. A 1 megohm resistor where a 10 kiloohm one should have been. Brown, black, green. A mistake severe enough to alter the circuit completely. Then a pulse. Then a pause. Then recognition. From that small error came a technology that moved through rejection, risk, and early failure toward long-term reliability. And that may be the most enduring lesson in the story. Not that invention is easy or solitary or inevitable, but that sometimes the future announces itself quietly, in the space between one pulse and the next. If you or someone close to you is struggling with health anxiety, overwhelming stress, or thoughts of self-harm, consider reaching out to a local medical professional, crisis line, or emergency service in your area for support.